So today I'm going to talk about two parts basically. The first part is the theory of the bilevel optimization. There's some algorithm involved in discussion of convergence and problems we can solve and so on. And then the second part of the problem will be on the more application side about this problem called inverse reinforcement learning. All right, so see, so these are our collaborators. So this line of research is being started back to 2018, 19-ish. So Jordan and Zhaoran, these two nice collaborators, brought to me the question of at that moment whether there is some relationship between bilevel optimization and a classical problem in reinforcement learning, which is actor critic. And then we started this line of research. And then later we see that indeed there are a lot of application in this area. So this is the first work I was mentioning. It's recently published in Science Journal of Optimization. It takes many years, but then it's good that finally it's got published. And then we have a few other NeurIPS papers and manuscript online about this line. Okay, all right. So let's get started. So bilevel optimization problem is basically can be described in this form, where you have two players. You can view it as two players or two levels. The upper level is the leader, and lower level is the follower. Right? So the leader, the optimization variable is both x and y. So for the lower level problem, you have a loss function g, and then you're optimizing with respect to y, and the x is fixed. All right. So then the optimal solution y star is a sort of a function of x. Okay. And then for the upper level problem, the loss function again involving both x and y, but then you're optimizing with respect to x. Now, since y star is a function of x, you basically can still view the entire problem as a single level, as a problem with a single variable x. But then, of course, you have this special structure that we need to take into consideration, right? So this kind of problem happens, for example, in game theory, where you have two players, leader and follower, right? So for the follower, which is the lower level, you're basically act the best you can based on your current information, right? So whichever the information you get from the other user, you just treat it as is and then optimize based on the best you can. Now, from the leader's perspective, you're not only fixing y, but you know that, okay, the follower is going to do this optimal, react optimally, so you can anticipate what the follower will do and then optimize, right? So he or she has more power over the choice of the actions, right? So that's why the red player or upper level player is called leader. Okay, so indeed, this kind of game, this kind of problem for game is called Stackelberg game in Nash equilibrium. At least it's closely related to the Stackelberg game in game theory. And then in mathematical optimization, this is a class of problem that's related to the MPEC, mathematical program with equilibrium constraints. There are a lot of applications. I'm going to talk about a few of those in this talk. In the second part of the talk, I'm going to talk about an application in inverse RL. So throughout the talk, the scenario of interest is the following. So the L function is smooth. And then G here, this G function is strongly convex in Y. Okay. The reason we want to make the strong convexity assumption is that this is, we just want to simplify things. Analysis will be much simpler. Okay. And then we'll talk about this extensions and other things later. And further, f and g here are stochastic functions, right? So they're not just deterministic, but they are expectations of something. So here, c is a random variable, so here fxy is the expectation of c, and then the loss function is fxy evaluated on this sort of a particular sample. Okay, so you can view this as a stochastic optimization problem where you have access to the samples. Okay. All right. Any questions about the problem setup? Okay.
So I just have a
Yeah,
short
go
question.
ahead.
Sorry.
Yeah.
So I wonder. So like you want this little L is smooth. Is that implied by the smoothness of the little f?
Yes. Yes. So it's a good question. So later we'll actually give sufficient conditions of whether this is smooth or anything, or other things. But f has to be smooth, and then G here has to be strongly convex.
Right. Right.
Yeah.
Okay.
Because otherwise, if G does not even have a unique solution, then non-smoothness or even non-discontinuity will happen.
Oh,
Yeah.
right.
But nevertheless, overall, with all the rest of the assumptions that we're going to talk about later, overall S is smooth at this moment.
Okay.
Yeah.
Yeah.
Okay.
Thanks.
All right. All right. So one application about this is the meta learning problem. So here the goal is to find to adapt to multiple training data set in order to achieve the best performance for individual tasks. So you have a central problem, but then you have multiple different tasks. You want to sort of adapt to different individual tasks. So here we have J tasks and data samples. And then here the bilevel formulation is the following. So the upper level objective is the empirical risk for all the training set. Right. So here is basically summing over all the data and all the set. And then theta star is the sort of the optimizer for that particular problem. Zi is the data. And then the lower level problem says that for each problem, for each task, I want to find a optimal solution for that as well. Okay. Now this, if you look at the loss function, this is not exactly the loss function for the particular task, but a linearized version. Okay. The reason is that first of all, if it's a loss function for the entire problem, it's highly non-convex, so it will be difficult to solve. Second, typically what people really want is that you have the ability to do quick adaptation, meaning if I do one step, just use one step or two steps, my solution will be able to adapt to the training set. So if you look at this problem, if you look at the optimal solution for this, basically the theta star will be just one step, more or less one step of the gradient descent. Okay, so that's meta learning problem. The upper level problem is the overall loss function, and then the lower level problem is the individual loss function. Okay. Another application is the so-called adversarial learning. Right. So the goal here is to train a model in a robust way to classify correctly the training samples, right? Even if there's adversary trying to temper it. Okay, so here the leader is a trainer because this is my main objective. I want to train a model well, and the follower is the adversary. Someone tries to act based on your current decision. Okay. Okay. So the bilevel formulation is the following. Well, at least it is one formulation of it. So if you look at the lower level problem, the adversary is trying to find its strategy, delta star, with its own sort of a loss function. Okay, we'll call it L attack. And then, so here theta, x and y, theta is the model parameter, x and y are the data. Okay, these are fixed for the adversary. So the adversary has basically saying that for a given set of data and given model, I want to find some strategy that try to destroy the model. Now for the upper level, now how does strategies destroying the model? So the adversary is the delta star is affected on the trainer's data sample. So x plus delta, this is you're trying to temper with the data. Y is the label. Okay, so here the adversary is trying to temper the data, but then the trainer, the robust trainer, wants to take that into consideration and try to minimize with respect to its model itself. So the L train is the training loss function, and theta is the model to be optimized. Okay, so Y is the label. All right. So again, here you can see that, oh, by the way, we have a constraint here. Delta is in a set C because we cannot assume that the adversary will have infinite power. So you will have like finite power, which means that the strategies, normative strategy is bounded by some constant epsilon. Okay. So overall, again, here we have dual objective, basically, right? So one main objective, which is I still want to train the model well, but then I want to take into consideration that there's some aspect of the problem that can be formulated into another optimization problem. Okay. All right. So there are many more applications in this domain, ranging from different machine learning applications and signal processing, for example, hyperparameter optimization, right? Again, here we have two sort of tasks. One is trying to find the best parameter, and second is trying to still train your model well. Neural architecture search, too. Here the goal is to find a efficient model, but then I want to reduce the number of parameters, active parameters, as much as possible, right? And pruning and so on. Okay. So many other applications. And then later I'm going to talk about in a little bit more detail about a reinforcement learning application. Okay. All right. So a little bit more into the mathematical formulation. So if you think about what the problem is, it's very closely related to finding the system of two equations, right? For finding the fixed point of a system of two equations, right? So you have two variables, x and y, and then basically have a system F, which is related to upper level problem. You have a system G, which is related to the lower level problem. You want to find x and y so that both of them are equal to 0, right? So where this equal to 0 coming from? This comes from the fact that G, x, y is related to the gradient of the lower level problem, so that if it's the partial with respect to y, if it's 0, okay, this says that the lower level problem is optimized. And also, the fxy, the other one, is related to the gradient of an upper level problem. Later, I'm going to come into detail about how to compute this gradient. But again, this is something that we want it to be 0. Right? So this means that, okay, the system is stable. Okay. So in classical work about this fixed points and stochastic problems, so what people usually do is the following, right? So we assume that each time I can sample a stochastic sample out of my distribution, right? So I can evaluate this f function at this particular sample, and then g function at a particular sample, right? So now suppose x is fixed, okay? Then we can do this kind of gradient descent type of update, choose a step size beta k, and then you can imagine that when k goes to infinity, this y star will be obtained. Okay, so for fixed x is fixed now. Okay, so you can imagine that this will be 0. Now, once this is done, you can fix y star, right? Fix y star, and then try to sample another. So try to go back to the upper another function, the other function f, and try to sample again, and then do this. Okay, but the problem here is that each time I sample epsilon k, try to optimize the upper level problem, I need to get an optimal solution from the lower level problem, which I need to do this infinite more times as well. Okay, so obviously there are some issues with this kind of strategy, classical strategy, and we call this kind of strategy a double loop algorithm, right? So you have a one loop that try to optimize the upper level, like objective or equation, and then that solution depends on the solution for the other one. Okay, so in classical work in stochastic control, there's something called two-time scale algorithm. Right? So what this says is the following. Now, instead of doing this double loop algorithm, what I'm going to do is I choose two step size, alpha k and beta k. Right? So I require that k, when k goes to infinity, the ratio between alpha k and beta k goes to 0. Right? So this means that beta k is an order faster, at least an order faster than alpha k. So beta k is larger than alpha k. Now, to our problem, what it means is that remember, this is related to the lower level problem. So it says that the lower level problem has to be faster compared with the upper level problem. Then there is a it's possible to avoid this double loop structure and then make the entire system converge to 0. Okay, so so here x update is the slower time scale, and then y update is the faster time scale. So they call this a 2 time scale stochastic approximation algorithm. Okay. All right. So now the question here is how does that really related to our bilevel optimization problem, and what kind of guarantees can we achieve? Okay. All right. So that completes the sort of a literature review, application part of it. Okay. Although the stochastic system of equations is not really an application, but then it's very closely related. Now, before 2020, there are a few works on this. So there are almost sure convergence, the one that we talk about. So this is basically these type of works are more asymptotic, right? So they talk about central limit theorem, and then when t goes to infinity, what will happen? And then there are works to talk about linear TTSA. This means that your function f and g are both quadratic. So your system is linear. And then there are a few finite time analysis of a bilevel stochastic optimization, but then later we'll see that the algorithm is mostly double loop, so they cannot avoid. So they need to solve the inner problem, the lower level problem, relatively accurately in order to go back to the upper level problem. Okay, and then this will incur some loss in terms of a sample and everything. Okay, all right. So so the plan is we'll first talk about our algorithm, and then talk about convergence analysis, and talk about some extensions, and then state of art, and then we'll go to the application. Okay. All right. Any questions so far? Okay. All right. So again, this is our problem. This is our bilevel problem. You can write it down as a mean Lx. And we'll assume that G is strongly convex in Y for any X in the feasible set. And then the question here is, can we calculate? Well, we can actually prove that this is differentiable by using this condition and assuming F is differentiable. And can we calculate the gradient for L to begin with? So if we can calculate the gradient for L, then probably I can just do a gradient descent on L. Okay. So it turns out that this is not very straightforward, but it's still doable. Okay. So what we can do is just take gradient with respect to x and do a chain rule, right? So first you take partial of the first element and then the partial on the second element. When you take a partial on the second element, you have to first, because this is also a function of y, you have to take the Jacobian out. Okay. Now the question is of how to compute this Jacobi. Okay. And then we using to calculate this Jacobi, we have to go back to the lower level problem and use the definition that this is an optimal solution for lower level problem. Right. So since this is an optimal solution for lower level problem, we can take a partial with respect to second argument and set it to 0. Okay. And then here, once you have this, we can use implicit function theorem because the solution is unique and everything. We can use the implicit function theorem to take a further derivative at a point of y star. Okay, so this is the solution, and then you see that now this y star is actually the same as this. This is Jacobi, so you can move this to the left and invert the Hessian, right? Okay, so now here the strong convexity assumption also appears because the Hessian here, it's a strongly convex, so Hessian is invertible, so can invert it back there. Okay, so then plug everything in, you'll have the gradient with respect to x. So I missed a y star x here. So it's this. Okay, so not only the partial with the first element, but also a relatively complicated term related to the lower level problem. This is how the upper level problem or the leader have the foresight, right? So where the additional information comes from the lower level problem. Okay. Okay. All right. So now the drawback of the above approach is that, of course, you need to calculate y star x all the time, which is the optimal solution, right? So this does not really give you an algorithm. You cannot directly use this as a gradient descent to optimize the original L. Okay, so so the idea here is that let's again go back to the stochastic system approach. Let's find two different systems, and let's try to find zeros for the system. Okay, so the first system is the upper level system. So it's basically the gradient for the upper level problem that we just calculated, and the G is a lower level system, which is basically the gradient, a partial gradient with respect to y, and I want it set to be 0. Right? So basically, we want this gradient and this gradient to be set to 0 at the same time. Okay, if I can find x and y such that these are true, then we're finding a so-called stationary solution of the system. Okay, so in this way, so we call f as a surrogate gradient for the entire problem, because f itself is not really the gradient, right? So the true gradient has to be evaluated at y star. Here it's evaluated at a arbitrary point y. So this is not the true gradient for the original problem, but we call it surrogate gradient. Okay. All right. Okay. So then can we not just directly apply the so-called 2-time scale algorithm and write things like this? Yes, you can. But then the question is, this sample, you see, this is a sample version of the gradient. This is a sample version of the lower level gradient. This is a sample version of the surrogate gradient. The first question is, it's not these gradients are not necessarily unbiased. Okay. The reason is this. If you look at the lower level function, yes, it's unbiased. It's easy because for any fixed x, I can sample a c and then perform an unbiased sample on c. Okay, that's easy. This is just regular stochastic optimization problem. However, for f, if you look at the expression, I can sample this function, I can sample this function, but then this is an inverse. This is a Hessian inverse, right? So if I replace this with a sample version and then invert it, the overall, so even if each sample are independent, each sample is independent, the entire thing, independent and unbiased, the entire thing will not be an unbiased estimator of the original fxy. Okay, make sense? Okay. So it's almost impossible to obtain an unbiased estimator for this, the function, the operator or the function f. Okay, but then the question is, so how should we proceed, right? So we cannot apply the like classical TTSA. Okay, so then we have the subroutine developed, which says the following. I can sort of draw p samples. P is a random variable uniformly drawn from 0 to t minus 1. So for each of the p, I will draw a sample of the Hessian. I will replace this red term with a stochastic estimate calculated in this way. Okay. So this is some constant, and then it's a it's a product of identity minus 1 over LG. LG is the Lipschitz constant for the lower level problem, and then the gradient samples, right? So this is a collection of sample calculated, a function of a collection of samples. And then for the rest of the terms, I can simply use the sample each of the functions, f and g and so on, okay? Okay, so it turns out that this is basically a Newman series approximation of the Hessian of the matrix inversion. If I do this, it turns out that we can show the following. So the bias between this estimate and the mean of the mean of this estimate and the function I want to approximate is bounded by 1 minus condition number. So mu g divided by LG is a condition number of the lower level problem to the order of t. T is the total, basically the average of the total sample we're going to sample for the Hessian. Okay. So as t goes to infinity, t becomes large, the error becomes small. And then we can also show that the variance is also bounded. Okay. So the bias here is reduced exponentially with respect to t. All right. So then the idea here is that we fix t to be in the order of log 1 over epsilon. The epsilon is some kind of error you want. So therefore, the bias is not too much. And then we do the following recursion, right? So each time for x update, I still use the step size alpha k, and then I use the estimate we just computed using the, so this h is this, okay? Just use this h. And then we update y based on the one step of stochastic gradient of the lower level problem. Okay. Okay. So the total number of samples we need here is in the order of t. So this is t plus one more sample here, and then like a couple of more here. So it's like order t samples we need. Okay, so which is log 1 of epsilon. And then we can use two time scale analysis to understand whether this process will converge and how fast this process will converge. Right? So recall that classical analysis not only requires that H and G, these two are unbiased estimator, but they don't have a rate analysis. They will just say that, hey, when k goes to infinity, this entire process will converge. Okay, so here we try to do a little bit more. Okay. All right, so the highlights here is that I will not go into too much of a detail, but then it's possible to analyze the rate of convergence. The condition here is gxy is strongly convex in y, and then we separately assume three different assumptions where Lx is either strongly convex, convex, and weakly convex. Okay, so we'll mostly just for sake of easy discussion, I will just mostly focus on the case where G is L is weakly convex problem, which basically means that it's a smooth. Just smoothness is enough. Okay, just assume that this L function is smooth. So in this case, this is our step size choice. You see, alpha k is k to the so capital K here is the total number of iterations we run. So the choice of alpha k and beta k are listed here. So you can see that beta k is bigger than alpha k. Okay, and then this specific order leads to the total number of samples we need is also k to the minus 2 over 5. Okay, and then so that's a sort of an overall result. Okay, so more specifically, these are the assumptions that we need. So we need to assume that the gradient for upper level problem, the gradient, a partial gradient of x and y are Lipschitz. And also the partial gradient of y is bounded. Assuming that lower level problem is strongly convex in y, and the Hessian exists, the partial Hessians are Lipschitz, and then Lipschitz and bounded. Okay, so this partial is bounded, and then these two are Lipschitz. Okay, and also with these assumptions, we can show that the surrogate gradient compared with the true gradient, the difference of this is bounded by L, the constant, times the norm of y star minus y, right? So what this means is that the difference between the true gradient and the surrogate gradient is bounded by how accurate your lower level problem is. If your lower level problem is solved more and more accurately, then these two will automatically become more and more accurate. And then this is in a Lipschitz manner. Okay, and then of course, and also the lower level problem itself is Lipschitz, meaning if I parameterize the lower level problem by x1 or x2, then their distance is bounded by how different these two variables are. Okay, and then we can also show that this Lx will be weakly convex with certain constant. This means that with this inequality, right? So mu weakly convex is basically means that the L function is smooth. It has second order derivative. Okay. All right. So so that's that. And we use two items to bound two different quantities to bound the progress of the algorithm. One is called delta y. It tracks how close the lower level solution is to the optimal solution based on the current iterates, right? Because we never solve the lower level problem precisely, so this is never zero. It will converge to zero, but never zero. But we need to know how close it is in order to do the analysis. And also we if the problem is convex, if we assume the problem is convex, then we use this delta xk to measure how the upper level problem is close, how the closeness of upper level iterates to the optimal solution. If the problem is not strongly convex, we'll just use the full gradient, the size of the full gradient, to estimate the progress of the outer level problem. Okay. All right. So we can show a few sort of recursion about these different quantities. I'm not gonna say too much about it. So basically, just for the main result, this is basically what we just showed in the table. The delta xk, this quantity, can be bounded by some constant times k minus 2/5 divided by a constant as well. So the thing that really matters is this quantity. And then you can also bound the inner problem, which is this as well, the inner optimality gap. Okay. So again, so these are sort of a basically first batch of first kind of result that we showed in a science paper just mentioned at the beginning. So the main intuition here is that the alpha k, which is the outer level step size, has to be slower, and then the lower level problem has to be faster because we need to balance the errors. We need this error, the lower problem error, to be faster, to converge faster compared with the other. Okay, so that's the main sort of intuition. And then if you recall that the rate we get is for the weakly convex problem is k minus 2/5. But then if you simply do a compare with an SGD problem, for what the SGD can do to optimize a smooth objective, the rate is k minus 1/2. So this number is smaller than this, okay, slightly smaller than this. So this means that the bilevel problem, at least when we did it naively, well, relatively naively, just one step of upper, one step of lower with proper step size control, it seems to be slower than the SGD. Okay, so that's the main message we get from that work. And then later we had some connection with actor-critic algorithm. Basically, we said that it's possible to show that the actor-critic algorithm in reinforcement learning is an instantiation of this bilevel 2-time scale algorithm. Okay, but then I will not discuss that in here. Okay, any questions so far? Okay.
Can I ask a question?
Yeah, sure. Yeah, go ahead.
If we were able to calculate unbiased estimates of the Hessian, how would that affect the convergence?
Good question. So here we will always assume that we are able to compute unbiased estimate of Hessian itself, but then the problem is this gradient itself, it's a Hessian inverse.
Yes, exactly. That's what I meant. Sorry, it's just like you said, it's
Oh,
almost impossible to obtain the unbiased estimate. But
Yeah,
if
yeah.
you were to able, if you
Okay,
were
so if
able
you
to
were
estimate it,
able to, then so basically, the sample issue goes away, and then the rest of analysis will still follow, right? Because here it does. So the main message here is that that doesn't really matter in the end because you only need to sacrifice that much of an error, right? So the error here is not that much. So in fact, that doesn't really matter as long as there's a couple of samples here, right? So yeah, so it doesn't really matter
okay. Thank
in
you
the
so
end.
much.
Yeah. Okay. Thank you. You will have a log factor of improvement, basically. Okay. Okay. All right.
Can I ask another question?
Yeah. Sure.
So you here you assume the the lower level is strongly convex. One
Yes.
reason, of course, is the smoothness of the upper level problem.
Yes.
But what I mean, what I'm trying to ask is, if the lower level is not strongly convex but convex, but you still know the upper level is smooth, so
Yes.
can the argument still follow, or
It can still follow. We need to be a little bit careful here, though, because the inversion, it's not very clear that you can still do the inversion. So we need to use a different way of
I see,
calculating the gradient. Yeah.
Yeah, sure.
So direct way still needed.
Yeah.
Yeah. Okay. But there are certainly other ways to deal with this.
Yeah.
Yes. Yeah. Okay.
Thanks.
Thank you. Okay. So let me just briefly talk about a few extensions in the state of art. So since we just mentioned that this naive like SGD kind of approach is relatively slow, so the question is whether we can further improve it. It's possible to improve it. I'm not going to go into too detail about it, but we could add certain momentum terms, which is highlighted in blue here, to both the upper and lower update, right? So if you look at lower, here it's a convex combination of the original one with the green one. The green here is the previous HKG, the stochastic sample, plus and minus the current and the previous capital G. Okay, and then here F is the same, right? So this is a combination of a current gradient and a momentum term. And then we call this algorithm sustain. So basically, we're trying to sort of reduce the error coming out of the gradient estimation. So the drawback here is that it requires reevaluation of the gradient at the same sample. So recall that here, Kasi are all the same. So this means that even for the previous iteration, I cannot directly use something out of memory, but then I need to sort of recalculate this G at the current sample. Okay, so that's the drawback of this. But then with this, we're able to show that if you use these step size, k to the order minus 1/3 and k to the order minus 1, you can get an optimal rate of k minus 2/3. So this rate matches the accelerated version of SGD. Okay. And then there are many other works, including Tianyi's work here, which actually made the single loop stochastic approximation algorithm work. So you look at the rate here, this is epsilon minus 2. So this exactly matches SGD, okay, without any acceleration, without any momentum, okay? So, and then a few other works. So what I would try to say here is that there, even for the simplest setup, there's a lot work and then a lot going on here just to look at this simple setup. Here, when I say simple, I meant the lower level problem is strongly convex, and also everything is unconstrained, okay? Now, a little bit of a more extension. So if we assume that this lower level problem is actually has constraints, then things becomes a bit more different, right? So for one thing, if you have a constraint, so I no longer know that for lower level problem, the optimal solution is, it's no longer gradient of G, partial gradient of G with respect to Y equal to 0, right? So this optimality condition is much more complicated, and then this will propagate back to everything else. And further, when you have constraint like this, this goes back to the very first question, whether this L is smooth or not, right? It turns out it's not, right? So it will not be smooth anymore, okay? So because of the constraint. So this will create a lot of the problem. So most of the analysis we did before may not work here, even just we add a simple constraint, okay? Linear constraint. But this is really important. For example, in adversary training application, we did see that you need to control the size of the adversary perturbation because it's not, it doesn't have infinite power, right? So we need to control it. Therefore, the constraint is really needed. So what we did was we have some recent work on this, try to make the entire problem smooth. What we did is to add a random perturbation here, where Q is a random vector and Y is the original variable. Okay, so there's a linear term in Y, but then Q is random. So by doing this, by selecting Q from a continuous distribution, it's possible to show that this entire problem, this perturbed problem is again smooth, at least differentiable, okay? And then we can start from there to develop algorithms, okay? I'm not gonna go into too detail about it. And then I will skip a few numerical experiments here because these are just for these particular experiments. All right, so in summary, we analyzed a very simple stochastic bilevel problem at this moment. So the goal is to develop a 2-time scale but single loop algorithm. Try to have one sample here, one sample here, and alternate, right? So that we make the algorithm very easy, right? Very easy to implement. But there's a lot of research recently, but then I think we're still scratching the surface. For example, what happens if G is not strongly convex in Y, or what happens if you have constraints and so on. So there are a lot of questions. You can easily make the problem very, very hard. Okay, so I think a lot of effort is still needed to understand the problem. Okay. So I will try to use probably 10-15 minutes to talk about the application, a little bit more detail about the application of inverse reinforcement learning. You will see that there's a nice application of this bilevel problem. Okay, so RL problem is basically a sort of an optimization problem, but then it has a time element in this. So it gives a reward function. We optimize a policy in a Markov decision process, right? So the agent will make decision, interact with the environment, and then make decision again. Here, inverse reinforcement learning is something one more step above this. Well, not above this, based on the RL, but then here the reward function, that how agent perceive the world, is still unknown. We also need to infer the reward function, okay? By a few data points, offline data points, expert demonstration. So we'll talk about this application. All right, so this is basically the diagram. So basically, the agent will be able to observe a lot of expert trajectories. For example, we're trying to learn how to drive a car, right? So the robot is how to drive the car. Then the expert trajectory will be a person driving in the city, and then record all the behaviors he or she has performed, right? So this is the expert trajectory. And then the learner will be able to get this trajectory and will be able to interact with the environment, and then try to output a good policy to say that, hey, at each turn, what should I do? At each different condition time, what should I do? And then how to drive the car from destination A to B. Okay, so this is the online sort of IRL. We'll mostly focus on this. There's a more subtle version of this, which you don't even have the interaction with the environment. Okay, so we'll not talk about that version. Okay, so the application of this, one interesting application of this is autonomous driving, right? So because it's very dangerous to just train an RL agent, just let it go directly on the road, right? So let it interact with the system, let it let it directly to drive on the road, right? So that will be very dangerous. So you want to collect a lot of human expert samples and try to sort of mimic how human is doing, right? Another application is the trading, right? So you want to mimic the behavior of try to figure out what's the reward function from a successful trader, right? Although the data may happen like in 2020, you probably doesn't really make sense to exactly mimic the behavior of the trader, but it is important to figure out what's its reward function, why it makes a preference, why it makes such a decision, what's his or her preference. Therefore, later when I start to trade today, I know how to make decision, right? So that's how this application about IRL is. And also one recent popular application is this ChatGPT, right? So there's one important training step in ChatGPT, which is try to utilize human preference. Okay, so how to make sure that the output of your training of the chatbot is aligned to the human preference. Human wants to this and this. This is a good continuation. That's a bad continuation. How to sort of incorporate that into the training. Okay, so I'm not going to go into too detail about this, but you could imagine that you need to somehow figure out the reward preference and reward from the human expert. Okay. All right, so in all the above applications, only learning a policy is not sufficient. So because the policy only works for the current environment, right? Stock market for a particular period of time, but then it's important to learn the reward function itself, so that we can easily transfer the knowledge to perform learning in a new environment. Okay, so that's the key for this. So therefore, we need to learn the reward, not just imitate the policy. Okay, all right. So let's just briefly go over the problem formulation. So here we have an MDP. S is the state, A is the action space, P is the transition probability. Basically says that current state, if you perform this action, what the world will transit to the next state, right? So this characterizes the environment. And then R, SA is the reward function. Gamma is the discount factor, eta is the distribution of the initial state. So the interaction between the agent and the environment is recorded by this trajectory. So you have an initial state, agent perform an action, what's the reward, what's the next state, and action and reward, and so on. Okay. And then pi at AS is the policy, right? So this policy basically says what's the probability under the current state of the world, what's the distribution of the policy? What's the distribution of action? Okay. And then pi E denote the policy from the expert, right? So we have this observation data. Okay. So so let's directly go to our proposed formulation, because of the time. So our formulation is the following, right? So you see here, there are two objectives again, right? So let's see. There are two tasks. The first task is optimize the policy, right? For a given reward function R, we want to find the best policy pi theta, which based on this reward maximizes the cumulative reward over t, right? So the reward function now is a parameterized version, right? So this is a neural network that parameterizing the reward. Now, once we have this policy, we need to find out what's the best reward. Okay, so how do we define the quality of a reward? Remember, we have the expert demonstration. So we want to make sure that the optimal policy you generated based on the current reward matches the expert demonstration, right? Okay, so therefore, you see, again, you have two problems coupled together, but then our main problem is task 2 here, which is trying to find the reward. Policy optimization here is just to help me find a policy that sort of guided me to find a reward. Okay, so again, there are two problems. This is a major problem. This is the sort of a minor or auxiliary problem. Okay, so what we propose here is to use the maximal likelihood principle. The action generated by our policy pi should be most likely if the ground truth is the expert policy pi e. Okay, so therefore you have this, we'll have this formulation where the lower level problem is finding the policy. Okay, you can ignore all this, what this means, but then basically this means that I try to, for given reward function, I try to find the best policy pi theta for the current reward. And then for the upper level problem, this means the expectation is taken with the expert policy. I want, so this is the max, this is the likelihood. This is a log likelihood function for the for my learned policy. I want this learned policy to match as much as possible to the expert policy. Basically, this says this. Okay, this is a maximal likelihood principle. So you see, again, you have two level problem. Lower level problem is the maximization. Upper level problem is, again, a maximization. But then overall, I want to find the theta. Okay, the theta is the x in my sort of a previous bilevel problem, like mathematical formulation of a bilevel problem. Okay, so here x is theta, pi is y. Okay, all right. So so that's the problem formulation. So it turns out that there is some special structure we could utilize for this particular problem. In particular, this policy function has some closed form. Although it's not, it cannot really compute it because the Q function itself is, you have to derive it recursively, but then you have a more or less a closed form solution for this. So we need to, so we can sort of utilize this this property. We can actually compute the gradient for the outer level problem relatively easily. So there is a closed form. I'm not going to go into detail about it, but you don't need to go into Hessian computation in this case. Okay, so the gradient itself is relatively easily computed relatively easily, although you still have two expectations. So you still need to do sampling and everything. Okay. So the idea then is the following. So first, you generate the policy, approximately generate the policy by performing the so-called soft policy iteration. Okay, so there's an algorithm for it, for the policy generation, which is called soft policy gradient descent or soft policy iteration. I just perform one step of it for the lower level problem, and then I go to the upper level problem, and then use my most current policy. This is my most current policy, just generated one step from the lower, and then just perform one step of, so sample one sort of a trajectory here, sample one trajectory here, and then perform a step, sort of a gradient ascent. Okay, so theta k here again is the problem parameter. Okay. All right, so this is the algorithm, and we're able to show some kind of convergence, convergence in terms of a gradient and everything. So again, because of this is a special problem, we're able to get a slightly better rate, not -2/5, but 1 - 1/2. But the idea here again is the same as before. We do one step, so single loop algorithm. We do one step of policy optimization, and then one step of the reward optimization. Okay, so the analysis derive basically from the TTSA analysis. Okay, and then so some okay, I'll quickly go over the numerical result. So this is the tabular grid world problem where the agent is randomly put on the grid, and then only this point has reward 1, and the rest of the places have reward 0. And we compare our algorithm with the classical algorithm called max-ENT. We see that the log likelihood is much better compared with the other one. And then we indeed can see that this is the reward map learned from max-ENT. This is a reward that learned from our algorithm, right? So in our case, most places are 0. We indeed learn a good reward. Only these two places have slightly higher reward than the ground truth. But then for the maxi-NT, you see every places are almost a 0.0, 0.1 or 0.2. Okay, so the reward they learn is also a bit worse. Now, we tested this on a robotic environment called MuJoCo. So there's a couple of different robots are doing different tasks. Okay, so this is our algorithm. The reward obtained by our algorithm. So these two are both ours. This is the reward obtained by expert, and then these are some state-of-art algorithms that try to find good policies for all these different tasks. Okay, so obviously our problem attained much higher reward than everyone else. Now, one interesting thing, the final experiment here is that our problem can find a reward that transfer better. What does that mean? What does that mean? That means if the agent is trained to learn an environment called this is an ant, healthy ant environment. So the ant has 4 legs, right? So you learn how to walk and go from destination A to B. Then after this, we learn the reward, and we try to transfer that to a scenario in a setting where the 2 legs become smaller, become smaller, right? So then the policy, how to walk, the policy will be different, right? But then as long as the reward is still accurately learned, I still know the preference, where like what kind of thing, where do I want to go, what kind of at a given place, where do I want to go? Like which place ideally what kind of a gate I want to take, or things like this. I can still learn much better. Okay, so we compare with all the rest of the algorithms with us, so we still learn much better reward compared with them. Okay, so although ground truth at this point is still very high, we're not very close to ground truth, but then we learn much better than the rest. Okay, all right. So to conclude, we talk about bilevel optimization problem. It is possible at this moment to provide some analysis to this bilevel optimization problem, but then I think it's still very limited, right? We need to make some pretty strong assumptions in terms of a problem class. Okay, but even with this limited theoretical analysis, we can still find some interesting application in, for example, in machine learning that can use the algorithms we propose to solve some interesting problems. Okay, because of time, I'll probably just stop here. Thank you, everyone. I will be happy to take questions.